Now here is a really good example of a double integral over a general region. Why is it a really good example? Well, it's a little bit more advanced than the other two, the previous two videos I posted, the part 1 and part 2. But sketching it isn't so bad because it's cylinders. So it's a nice introduction into maybe a little bit more advanced problem. And so the first thing I'm going to do is just figure out what's going on. What am I trying to do? First, I'll point out that these are both cylinders and they have a radius of 3, right? Because the equation of a cylinder is x squared plus y squared equal to the radius squared. And so the radius must be 3. So here we have a radius 3. And now I am looking for a volume. So I'm thinking that I should be using this in some way. So remember that this is the volume below the surface z equal to f of xy and above the general region d. So I'm going to try to make this formula work out for me. What I'm going to do is first sketch this solid that I get when that's bounded by the cylinders. So sketch of the 3D solid. Now I will admit that I am one of those teachers that every 5 seconds says, now I'm not an artist. And that is because I am not an artist, but I am going to do my best to get a good sketch of these cylinders. And so let's go ahead and draw this out here. Here's my z-axis, my x-axis, and my y-axis. Hopefully you don't mind the way I've labeled it. Sometimes people switch the x and the y, I think. But this is just the way I do it. So let me go ahead and sketch these cylinders. I'll let this one be red, and I'll let this one be green. Okay. So at some point in your class, I would think you would have talked about sketching quadric surfaces and cylinders. So we'll have to kind of tap into that information, but we can make it pretty easy. So let's look at the red one first. So my radius of my cylinder is 3. And so first, let's just pretend I'm in the XY plane only. I'm just going to draw a circle. And pretend, I'm not really going to make it super accurate, but I'm going to say, I'm going to pretend this has radius 3. Now Z in this equation isn't fixed, meaning Z can be whatever. And so this circle gets extended down the Z axis. And so when you're sketching a cylinder, whatever variable is missing is actually the axis that it's going to be centered at. Okay. Now I'll take my green. I'll sketch this other one. So same idea. So because x is the variable that's missing, x actually isn't fixed. It can be whatever it wants to be. And so it extends along the x-axis. And so my cylinder actually has the center as the x-axis. So other cylinder, this. Okay. And I want the solid that is enclosed by the 2 cylinders. So let's pick another color, blue. So I'm going to have this cylinder kind of cutting into my other cylinder. And I end up with this general region D. Okay. So I'm just going to look at my general region D in the XY plane. Okay, so before we do that, let's think about this equation again, or sorry, formula, whatever you want to call it. First, what is the surface f of xy? Remember, we have z equal to f of xy. And so I'm going to use the second cylinder and solve for z. So I have a z equal to a square root of 9 minus y squared. Now we would get a plus or minus, but I'm only going to look at this piece here that I drew the blue region D. So I'm just going to go ahead and let it be positive. So this is going to be my f of xy. Okay, so I'm going to save this for later. And now I'm going to use this first cylinder to give me my region D. So here I'm going to sketch D. And I'm going to use that x squared plus y squared is equal to 9. Once again, I'm only going to do this one piece. That's not everything. That's not my whole volume, but it's just the one piece I'm going to use because otherwise we have symmetry and we can just multiply it to get our whole volume. So let's go ahead and sketch this region D. I'm only doing part of it. So x squared plus y squared should be, right over here, a circle with radius 3. But I'm only going to do a quarter of my circle. So it'll look like this, where this is 3 and this is 3. Okay. And so this is x squared plus y squared equal to 9. But then it's also bounded by these axes. Okay. So I'm actually in good shape now. I can go ahead and set up my double integral. But we do want to be careful. I need to figure out what my limits of integration are. So I'm going to be integrating. I'm going to call this volume 1, and I'll tell you why in a second. I want to integrate over this region D, and what I'm integrating is this surface square root of 9 minus y squared. Now here's where we get to be a little bit careful. What would I like to integrate with respect to? So I'm either going to have dx dy or dy dx. Again, let's come over here to the side. Say I'm integrating 9 minus y squared, square root of 9 minus y squared dy. This can be done. It just won't be very fun because we'd have to use a trig substitution. So I'm not crazy about that. I would rather integrate with respect to x, because then this is just a constant and I just get to tack on an x. And so this one I like better. So I'd like my order to be dx, dy. And what does that mean? The outer integral always depends on constants. And the inner integral always depends on the curves. And so now I can get my limits of integration. So I want to bound y by constant values. So y, the lowest point of y is when it's at 0 at the bottom. And the highest point of y is when we're at the top of our quarter circle 3. And now I'm going to put a bound on, or 2 bounds, obviously, an upper and lower bound on x. So I want my leftmost curve and my rightmost curve. So I'm thinking of x, so I'm going from left to right like this. So my leftmost curve is here at y equal to, or sorry, x equal to 0. My rightmost curve is the circle here, right? My blue curve. So I'm going to have to go ahead and solve this as a function of y. This would be the same thing as writing x equal to the square root of 9 minus y squared. Again, we're keeping it only as the positive, and so I'm just going to leave it as the positive here. And there we have our limits of integration. And now we're ready to integrate. So I am going to come back up to that picture to explain why this isn't actually the entire volume. So again, I'll call this V1. And now let's go ahead and put in our limits of integration. So the outside should be the constants and the inside should be the curves. And you'll see why this order of integration was beneficial to us. It makes things way easier. So by design, I chose it to be this way on purpose. My inner integral is with respect to x, right? These were the limits of integration or the bounds that we put on x. And the outer integral, which has the constants 0 to 3, are the bounds for y. So let's go ahead and evaluate our inner integral. And look how nice this is going to be. We are integrating with respect to x. So y is just held constant. And so the square root of 9 minus y squared is just a constant. And so I just get x square root of 9 minus y squared. Evaluated from 0 to the square root of 9 minus y squared. I am going to point out that these are my limits of integration. They are values of x. And so we're going to plug these in for x and we just leave y alone, right? Right now we're pretending, meaning we're holding y constant, and so the y just stays. And so first, I evaluate at my upper limit. This is going to get plugged in for x. So I get square root of 9 minus y squared times the square root of 9 minus y squared. And then over here, when I plug in 0 for x, I just get 0. And then this nice magical thing happens where our inner integral comes out to be equal to just 9 minus y squared because the roots here simplify each other. So this is our inner integral. And remember, we take that and we plug it into where the brackets were. So we have evaluated the entire inner integral, but I need to put it back into the 0 to 3 dy. And that was just so much easier than doing a trig substitution. It was really worth it to think about which order of integration was better. I get 9y minus y cubed over 3 from 0 to 3. And then of course, these are y values because I'm integrating with respect to y, but y is the only variable left. So I think that's kind of obvious. When I fill in y equal to 3, I get 9 times 3 is 27. And then I get 3 cubed, which is 27 over 3. Minus, then when I fill in 0, I get 0 minus 0. So I get 27 minus 27 over 3. Oh, we could simplify this. We can combine the fractions. So let's put them both over 3. Well, this one's already over 3. And 3 times 27 is 81. I hope. Seems accurate. And now we can combine these. So 81 minus 27 will be what? 54 over 3. Oh, and that actually is divisible by 3. Isn't that nice? So 54 divided by 3 is 18. Okay, so this is our answer for V1. I am going to circle it, but it's actually not the whole answer. And let's see why. So let's scroll back up to our picture and see what we need to do. So look at what I did for my region D. I only included this one portion of my circle, the positive part, right? And the same thing for my surface. I only looked at the positive square root. And so I'm only looking at this region D in octant 1 that extends up, right? And I just got the volume here. Now that's okay, but that's not everything. So this extends back, right? And this extends. So I have 8 octants. I'm only finding the volume of 1 of my 8 octants because I assumed that Z was positive, meaning I'm only on the upper Z half. And then I only took a quarter of my circle. And so I'm only getting an 1/8 of the total volume. And so I'll come down here and say this was perfectly fine. And because it's all, symmetric to each other, all I need to do is say that my volume is actually 8 times V1. I hope that you agree with that or understand what I'm saying. So we just get 8 times 18, which is, 8 times 18 is what, 80 and 64, 144. And there we have the entire volume.